All right, guys. So we're going to kind of switch gears, and we're going to start looking at periodic trends. These are going to be different kind of properties that elements and compounds will have based off of their location on the periodic table. And with that, it's going to lead us into looking at polarity, which we mentioned earlier this week. But we'll be able to determine if a compound is polar or non-polar based off of some of these trends. Our first trend we're going to look at is electronegativity. Electronegativity is the ability of an atom of an element to attract electrons when the atoms are in a compound. So if something has a high electronegativity, it has a very strong pull on those electrons. If it's a weak electronegativity or a lower electronegativity, it has a weak pull on the electrons. The overall trend for electronegativity is that it decreases from top to bottom in a group. So going down a row on the periodic table, it gets smaller, or excuse me, a column, and it increases from left to right across the period. So these wedges will kind of make sense a little bit more later. But overall, that means that our highest electronegativity is going to be towards that top right corner. Is going to be the highest. Now, with electronegativity, it said that it has to attract electrons when atoms are in a compound, so when bonded. Our noble gases, remember, are stable and they tend to not bond. So this does not include noble gases. So on the periodic table, the element that's in that top right corner that is not a noble gas is fluorine. So fluorine is the element that has the highest electronegativity. This can kind of come up. We've seen it in the past on where we had state tests. This would be a trick question where they would ask which element is the highest electronegativity, and they would have both fluorine and helium, but you had to remember that helium was a noble gas, so did not have an electronegativity value. All right. So how this relates to polarity. Since we said that some atoms can attract electrons more if they're more electronegative, we end up where electrons are not always shared equally in that covalent bond. So if two substances have about the same electronegativity, they can end up making a nonpolar covalent bond where the electrons in the covalent bond are shared equally between the atoms. All of our diatomic molecules that we talked about, those are nonpolar, because like oxygen, O2, one oxygen is not going to be more electronegative than the other oxygen. So they are going to share equally. The nonpolar covalent bonds, and these also tend to be very symmetrical since the electrons are shared equally between the two atoms. What we also end up with are polar covalent bonds or polar bonds. These are covalent bonds between atoms that do not share electrons equally. So atoms that have different electronegativity values are not going to share electrons equally. One of them will be more electronegative or stronger than the other and kind of hog all of the electrons. These are going to end up being non-symmetrical, with one side being larger or having more electrons than the other. The more electronegative atom is going to attract electrons more strongly and gain a slightly negative charge. And we denote a slight negative with that delta negative sign. And the less electronegative atom has a slightly positive charge with that delta positive sign. So you can kind of see this. If you look at the image in the bottom left, it does show you that our diatomic ones, where we have like our 2 hydrogens and 2 chlorines, they are truly balanced. One of them is not more electronegative than the other. It is going to end up being symmetrical. The blue circle is kind of showing the electron cloud, where all of the electrons are in that place. However, if you combine a hydrogen and a chlorine is towards that top right corner, whereas hydrogen is towards the top left corner. Chlorine is more electronegative than hydrogen, so chlorine is going to kind of hog all of the electrons, ending up with the chlorine side being larger than the hydrogen side. So it's kind of hogging all of those electrons. The table on the right, you'll see one similar to this in your homework. This is just showing you each element and its electronegativity value. So where we would normally have the mass on a periodic table, here it has the electronegativity value. So you can see that like fluorine has the highest electronegativity, whereas francium in that bottom left corner is the lowest electronegativity value. So you can kind of see that gradual increase going from the bottom left corner to the top right corner. And what we do with these numbers, those electronegativity values, we can subtract them to find the electronegativity difference. And that's going to tell us what type of bond we're dealing with. And this is something that you will do on your homework. So when we subtract that electronegativity, if the difference is anywhere from 0 to 0.4, that's a very small electronegativity difference. They're pretty much going to be the same electronegativity. And that will end up resulting in a non-polar covalent bond. And make sure that for it to be a non-polar covalent bond, it has to be made of 2 nonmetals. You'll see that there are some exceptions where it might be a metal and a nonmetal that are very close together, but a metal and a nonmetal cannot make a non-polar covalent bond. So nonpolar can only be covalent bonds. Polar can also only be covalent bonds. So if when we subtract the electronegativities, it's greater than 0.4, but less than or equal to that 1.7, there's a good difference in electronegativity there. That is going to end up in a polar covalent bond. And yet again, it has to be between 2 nonmetals. Now, if it is greater than 1.7, it tends to be ionic. And remember, ionic is going to be between a metal and a nonmetal. Like I said, we can do the electronegativity difference, but these ranges are not always going to work, simply because you might have 2 nonmetals that have very different electronegativity values, but they're still considered polar because they're 2 nonmetals. Or we might have a metal and nonmetal where the difference is less than 1.7, but a metal and a nonmetal can only be ionic. So let's look at one of these. I'm going to go back a slide. That way we can look at those electronegativity values. So if we were dealing with, let's say like CF would be a bond that we're dealing with. We would subtract the 2. So fluorine, those numbers are kind of tiny, but fluorine is 4.0. Carbon is 2.5. So if we subtract those, that is 1.5 is our electronegativity difference. So this would be a polar bond because it is between 2 nonmetals. And it's that kind of between 0.4 and 1.7. Whereas if we had So I'm trying to find a good example. If we had like chlorine to bromine, I'm going to do this one at the bottom. Chlorine is 3.0, bromine is 2.8. So that is a 0.2 difference. So that would be a nonpolar covalent bond. So you're simply doing a subtraction of those electronegativity values and seeing which range it falls in. But like I said, make sure to double check. If it is two nonmetals, it's either polar or nonpolar. If it is a metal and a nonmetal, it is ionic, even if it does not match up with the range. So with the presence of those polar bonds, this can make our entire molecule polar. So if you remember when we talked about properties of molecular compounds or covalent bonds, we said they can be polar in nature. So polar molecule, we're going to end up with one end of the molecule being slightly negative and one end of the molecule being slightly positive. So because the electrons are not shared equally, we end up with a negative end and a positive end, similar to like a magnet would be. These two ends can act as poles, so like a magnet. And we say that they will have what we refer to as a dipole. So di means two. So this is going to be a molecule that has two poles. So a molecule that has a positive end and a negative end. And these tend to react with other polar molecules or even magnetic fields they can act with as well. So when polar molecules are placed between oppositely charged plates or magnets, they tend to become oriented or aligned towards the positive and negative plate. So all of the positive ends of the molecules will kind of be facing the negative magnet, whereas the negative ends of the molecules will all face the positive magnet, since those opposite charges attract one another. And how we tell if the molecule as a whole is going to end up being polar, there are a couple things that we look at. First, we look and see, does this molecule have polar bonds? So does it have atoms that have that difference in electronegativity? If it does have polar bonds, we then have to look at its molecular geometry or shape and see if the shape prevents polar bonds from canceling. So polar bonds would need to pull against other polar bonds, kind of like a tug of war, to cancel out. And there are certain shapes that tend to allow for the molecule to be polar versus non-polar. So we're going to relate this back to your Vesper shapes. That way you can see if it's polar or non-polar. So our geometries that allow for polar bonds to cancel, these are going to be the shapes that are also molecular geometries. So the ones without dots on the center tend to be non-polar. Now I say tend to be because there are always exceptions to the rule. So like something that's linear. So one thing that we have drawn that's linear is carbon dioxide. And I'm just going to sketch it real quick. So here we can see if we're looking at carbon and oxygen, oxygen is further to that top right corner. So oxygen is more electronegative. So all of the electrons are going to be pulled towards the oxygen from the carbon. That's what you see these arrows representing. Well, the other oxygen is also kind of pulling electrons from the carbon. So these two are able to pull against one another, allowing those polar bonds to cancel out. So this ends up being non-polar. For trigonal planar, same kind of thing applies. If there are not dots on the center atom, it allows all of those to pull against one another and cancel out. Same thing with tetrahedral. Where I said that there are exceptions to everything, I'm going to put on here for nonpolar. Outer atoms must match. So it is possible that you have something linear that is polar if those outer atoms do not match. So I'll draw like hydrocyanic acid or HCN. Looks like this. Whenever we're looking at electronegativities, carbon is a slightly higher electronegativity than hydrogen, but nitrogen is more electronegative than carbon. So all of the electrons are kind of being pulled towards the nitrogen. So since those forces are not pulling against one another, this would end up being polar, even though it's linear. So these are kind of general shapes that tend to be nonpolar, but like I said, if those outer atoms do not match, it tends to end up being polar instead. And then we get to the shapes that do not allow polar bonds to cancel. These are going to be the ones that have dots on center atom, or the ones where the outer atoms don't match. So like if we have a bent structure, so water, whenever we drew it, looked like this. Well, if we are looking at those electronegativity values, oxygen is more electronegative than hydrogen. So the electrons are being pulled towards the oxygens. But notice that since they're bent, they are not straight across from one another. So they are not pulling against one another. And there's nothing pushing in the opposite direction. So it ends up being polar. Same thing with trigonal pyramid. One of the things we do that was trigonal pyramid was ammonia. So looking here, nitrogen is more electronegative than hydrogen. So all of the electrons are being pulled towards the nitrogen, but there is nothing going in the opposite direction from that electron pair. So that ends up being polar as well, with those not being able to cancel. So once you draw the dot structure, you can kind of guess if it is polar or nonpolar. So I would first check and see, are the outer atoms all the same? And if it is that linear trigonal planar tetrahedral with all atoms the same, they're not dots on the center atom, it tends to be nonpolar. Whereas if there are dots on the center atom, or those outer atoms are different, it is going to be a polar structure. All right. And with our molecules that are polar and nonpolar, a lot of times this goes into solubility and looking at if substances will dissolve in one another. Polar molecules are only soluble or can only be dissolved by other polar molecules. So polar molecules can interact with other polar molecules. Non-polar molecules will interact with non-polar molecules. So you may have heard the term like dissolves like. How this works, the picture in the middle with the blue background, if you've ever washed your own dishes or done your own laundry, you'll kind of know that if you do not use soap, it doesn't get clean. Same thing whenever you are trying to wash your hands. If you don't use soap, you're not actually cleaning your hands. And that's because soap are the little black structures. They have a polar head and a non-polar tail, similar to your lipids in your phospholipid bilayer that you talk about in biology that had that polar head and the non-polar fatty acid tail. Your polar head of the soap will attach to water, but the non-polar tail will attach to the dirt and oil. So whenever it rinses and the water drains, it actually pulls the oil from the dishes or the clothing. And we're going to stop here and continue with the rest of the trends tomorrow, or excuse me, on Monday, as well as looking at the intermolecular forces that occur between molecules.